This is lesson 5.1, Properties of Exponents. When we talk about exponents, we're talking about the little number that's above the base number. So this is called the exponent, and sometimes it's called a power. So I could call it a power, or I could call it an exponent. The number that is the big number at the base of the problem is called the base number. So in my first example here, a is my base, m is my exponent. In my second example, b is my base, n is my exponent. And I could say exponent, or I could call it a power. There are several rules to how to deal with powers, and the reason we need these rules usually is to simplify things with variables. But a lot of my examples at first are going to show numbers because they're a little bit easier to understand. So rule number 1 is a to the m times a to the n equals a to the m plus n. So what this rule says is if I have two different exponents and the same base, then I'm going to add the exponents. So in my example, if I have 5 to the third times 5 to the second, that's going to be 5 to the 3 plus 2 power, which is 5 to the 5th. That's the rule for my exponent. The second rule is 1 base and 2 exponents. And this is often called the power to a power rule because you have a power inside and a power outside. And the rule says if I have a power on the inside of the parenthesis and a power on the outside of the parenthesis and I only have one base number, then I'm going to multiply those exponents. So if I have 3 to the second power to the third power, I have 2 powers, 1 base. So I keep my base and I'm going to multiply 2 times 3. So that's going to give me 3 to the 6th power. The next rule is if I have something multiplied inside parentheses and then the power goes to both of those. So this is a times b to the m power. So sometimes you can't multiply the a and the b, so we're just going to put each of these individually, a to the m power and b to the m power. We're just putting the exponent on each of the variables on the inside. So example of this is if I had 2 times x inside the parentheses to the second power. Well, this would be 2 to the second power times x to the second power, or I could even go ahead and write this as 4x squared. Rule number 4 is the negative exponent power. If I have a negative exponent, I can rewrite my power as a positive exponent by rewriting this whole problem. So if I have a to the negative m, I can rewrite it as 1 over a to the positive m. This one was negative, but this one is positive. So if I have 7 to the negative 2, I can write it as 1 over 7 to the positive 2 power. And I could even go ahead and say that's 1 over 49. Rule number 5 is the 0 exponent power. If you have 0 as an exponent, it doesn't matter what your base number is, it's always going to be 1. Always 1. So for my example, if I have negative 89 to the 0 power, that equals 1. So any number or any variable to the 0 power always equals 1. Rule number 6 says if I have the same base, so I have a to the m divided by a to the n. The division tells me to subtract. So I keep the base a and I subtract the exponents m minus n. So for my example, I'm going to keep the base 6 and I'm going to subtract top minus bottom, 4 minus 2, which would make this be 6 to the second power. And if I wanted to, I could even go ahead and say that's just 36. The last rule is if I have something divided and then to the power. So a divided by b is grouped together and then it's to the m power. So I'm basically putting this power on each of the variables. So a to the m divided by b to the m. So if I had the example of 4 over 7 squared, I would rewrite this as 4 squared over 7 squared, and then I could go ahead and even say this is 16 over 49. And those are the rules. Now a lot of times the rules are going to be mixed up. They're going to be used together in combinations. So these next examples are going to have combinations of rules. So my first problem here, I have negative 4 times 2 to the 5th power. It's in parentheses and it has a square on the outside. So I am going to distribute that square to each of the powers. Remember, this is 4 to the 1st power. So negative 4 is now going to be to the 2nd power, times 2, which is going to be to the 5 to the 2. This makes it a power to a power, so that makes 10. So I have negative 4 squared times 2 to the 10th. I have 3 examples on this page. The first one is power to a power, which means multiply. So 2 times 3 is 6. The next one has 2 bases. So if I have 2 separate bases, then I'm going to add the exponents. So this is negative 8 times negative 8 to the 3rd, which means negative 8 to the 1st power times negative 8 to the 3rd power. These will be the 2 powers I'm going to combine. So I have negative 8 as my base. 1 plus 3 is 4. On the next example, I have 2 divided by 9 as a group, and then it's to the 3rd exponent. So I'm going to distribute my exponent and make this 2 to the 3rd over 9 to the 3rd. And I could even go ahead and simplify this as 8 over 729. But you don't have to. You can always use your calculator, though, to find out what these are going to equal. Alright, so the most important reason that we need these rules is because of variables. So the next few examples are all going to have variables. For this first one, I have b to the negative 4 times b to the 6 times b to the 7. So I have the base listed individually each time, so I add. Negative 4 plus 6 plus 7. So that's 13 minus 4, which is 9 for my exponent, and I keep my base. So altogether, this adds up to be b to the 9th power. For the next problem, I have this group to the negative 3 power, so I'm going to distribute the negative 3 first. So that's going to be r to the 6th, because negative 2 times negative 3 is 6, and s to the negative 9th, because 3 times negative 3 is going to be negative 9. Now this is where some people have some difficulty. If I have a negative in the exponent, basically what that means is where it is, the exponent's negative. So I can move this to the numerator and make this be r to the 6th times s to the positive 9th. And now the negative exponent is gone, and I've moved the s to the numerator. If it had been a negative up here, then this would have moved down. So in this next example, I'm looking at several different things together. The first thing is I'm kind of going to group some things. So 16 divided by 2, and I have m to the 4th, and I have n to the negative 5th divided by n to the negative 5th. So keep in mind that numbers, like 16 divided by 2, numbers are still numbers. So 16 divided by 2 is still 8. I don't have to subtract. There's not any special thing there. It's just a normal number. M to the 4th has nothing to combine with, so it just stays m to the 4th. But n to the negative 5th divided by n to the negative 5th. Well, I keep the base, and I take negative 5 minus negative 5. Negative 5 minus negative 5. Two negatives become positive, and that's 0. Negative 5 plus 5 is n to the 0. So we talked about in one of the rules, anything to the 0 power is 1. So this is 8m to the 4th times 1, but we don't need the 1 to be written, so we just write it as 8m to the 4th. In the next example, the numerator has a power, but the denominator doesn't. So I'm going to go ahead and simplify the numerator first and make this x to the negative 6, y to the 9th. Keep in mind these are powers. In a situation, power to a power, power to a power, and we always multiply when it's power to a power. I have done nothing to the denominator, keeping it like it is. Now, I'm going to look at this in terms of groupings. I have the x's and I have the y's. Since they're divided, I'm going to keep the base and subtract the exponents. Negative 6 minus 4 is negative 10. Keep the base for y. 9 minus 9 is 0. So, x to the negative 10 can be rewritten as 1 over x to the positive 10, and y to the 0 can be rewritten as 1. But since we're multiplying by 1, we don't have to change anything. So this problem simplified to become 1 over x to the 10th after we combined the like terms through division. Alright, this problem looks like it's harder than it is. There's not an exponent here and there's not an exponent here. So this is really just 7 times y squared times z to the 5th times y to the negative 4th times z to the negative 1. They're all just multiplied times each other. Multiply, multiply, multiply. So I can actually rearrange this and make it 7. I can put the y's next to each other, and I can put the z's next to each other. And the reason that makes it easier for me is because 7 doesn't combine with anything, but if I simplify the y's together, I keep the base, I add the exponents, so this is 7y to the negative 2. Same thing with z. I keep the base, I'm going to add the exponents. 5 plus negative 1 is 4. You might think that I'm finished, and I almost am, but I never want to keep an answer with a negative exponent. So remember, if you have a negative exponent in what's considered the numerator, you can move it to the denominator. So the 7, I'm not changing. The z to the 4th, I'm not changing. But I am moving y from the numerator to the denominator. And when I move from the numerator to the denominator, notice that the exponent changes from being negative to being positive. So this is 7 z to the 4th over y squared. Okay, last example. This has a lot of things to it. Notice the grouping with the power on the outside. So the very first thing I'm going to do is distribute the 3 to every single power. So that makes x to the 12th, y to the negative 6th, x to the 9th, y to the 18th. And keep in mind that I am multiplying this. Power to a power, power to a power, power to a power, power to a power. Okay, now what do I do? Well, I'm going to group them. I have x's together, and I'm going to keep the base, and I have division, so I'm going to subtract the exponents. 12 minus 9 is 3, so I have x to the 3rd. For y, I'm going to keep the base, y, and I'm going to do negative 6 minus 18. Negative 6 minus 18 is negative 24. So, this is great, except I have to move that negative exponent. So y to the negative 24th is going to move to the denominator, and the 24 is going to become a positive exponent.